Salutations, everyone. Let's look at these homeworks from Euler's method. It's a bit ugly number crunching, part of it at least, but of course part is also set it up correctly. And let's focus especially on setting it up correctly rather than the actual numbers that we crunch here. So number 3, that was y prime plus 3y equals x squared minus 3xy plus y squared, and we want to do y0 is 2, and we take steps of 0.05. Okay. Okay. So, well, you could ask, what kind of equation is this? Well, it's not a linear equation, and it's not a Bernoulli equation, and it's not one of these so-called homogeneous ones. So exact, I don't know exact. It doesn't look exact to me either. So I think none of the methods that we have applied to this one. So let's use the Euler's method. First of all, we have to write it in the right form. For Euler's method, we have to write it in this form. So we have to isolate the y prime. So this is actually minus 3y plus x squared minus 3xy plus y squared. Okay. Good. So what do we need to do? So we our x0 is 0. We started. Where do you know the value for x0? Well, that is where we start. Okay, this is x0, and this is going to be y0 too. So y0 is 2. That's the setup. And then we have the formula. X1 is x0 plus h, and h was 0.5, so this will be 0.05. Sorry, I said 0.5, I mean 0.05. And what is y1? Here is where we actually have the formula, right? y1 is y0 plus h times p x0 y0. Okay, plus plug it in, 2 plus 0.05 times, and now we have to plug in these two values inside here. So perhaps let's make the table again. So this is xi, this is yi, and this is p of xi, yi. That's the things that we need, and these are the steps. The initial step I equals 0, then we have just, what we said, 0, 2, and we're now calculating, we need to calculate this guy, and so what is that? We plug in 0 and 2 in this expression. Okay, so p of 0 and 2. Everything with x is gone, because it's 0, so we have a minus 6, we'll put 2 there, plus 4, so I get minus 2. So this is 2 plus 0.05 times minus 2. That is 2 minus 0.1, right? Twice 0.05, so that is 1.9. At this point we could have done it. We don't need to calculate. It's the next step always that we need to calculate, right? So y2 and the next steps. What is y2? So okay, let's complete the row that we have. X1 we have now calculated to be 0.05, y1 we calculated to be 1.9. Well, we need to calculate this guy, so perhaps let's calculate this guy first. Okay, so that one we need Wolfram alpha. So I'm gonna have to, or a calculator, or an Excel, or a table, or whatever way you do this. So now the problem is, for instance, with calculator, is that calculators can make tables of functions of one variable. With two variables it gets a bit trickier. So I'm going to use just Wolfram alpha. Sorry, I have to make sure copy this, because otherwise I cannot go back here. So x1 is going to be 0.05, and y1 is 1.9. Right, and that I have to plug into my p. I'm calculating the number here that goes in the table. I have to calculate another thing, but let's do it in steps. Okay, so here I have to put in this expression minus, give me a sec here, minus 3 times y, which is 1.9, 1.9 plus x squared, which is 0.05 squared minus 3 no, that's not the 0, that's an O, 0.05 y, which is 1.9 plus y squared, and y was 1.9 squared. Let's see. Let's first see that this is what I wanted him to compute. I think that's what I wanted him, minus sign there. Yep. And so he says this is equal to, let me record this here, well, minus 2.3725. Okay, so I'll go back. So we plug this in here. This is minus 2.3725. Let's do 4 digits. Okay, so this is our line, the row for the x1, y1, and that. So that's all we need for y2, because the formula for y2, let's write it up, is it's simple, right? The next y is calculated using the previous row. Okay, so of course, but we can already plug this in. What is this going to be? Well, x2 is going to be another 0.05 added to it. The next thing we need to calculate is y1, and that's what the formula comes from. And we, as I said, we do this using the previous row. Okay, so that we're using the values that comes from this row and plug this in here. So y1 is 1.9 plus h, that is what was h, 0.05 times this p, the value, that's this value that we just calculated, right? Minus 2.3725. Now we have to calculate this. That one I'm going to not calculate with Wolfram Alpha, but with my calculator, because that's much easier, right? It's just, so I do 0.05 times 2.3725, and then I subtract that from 1.9. And I get 1.7, I hope I did not punch in something wrong here, 1.7814. I'm going to round up to the next digit, fourth digit here. Okay, so that's the y2, 1.7814. And then the question said also do the third one. Okay, let's do this. So we need to calculate now what? Well, we need to calculate the p with these two values. Now, my x2 is 0.1 and my y2 is 1.7814, and we have to plug this back into this expression here, and that's why I like to write it this way, because now I only have to change whatever is within my parentheses, right? The 1.9 is now 1.7814, the minus is all that is part of the formula, then this becomes 0.1, that was the x. This x is, as I said, 0.1, and the 1.9 is supposed to be 1.7814, and here also 7814. So let me see, is this what I want? I have to plug in. Now, copying, I'm working with a paper and two different iPads here, so I might copy something wrong at some point, but let's assume, I hope for not, and so I get as an answer minus 2.6952. Okay. So we said this was minus 2.6952. By the way, if we're taking small enough steps, remember these are the slopes that we see in the direction field, right? These are the slopes of these little vectors, and clearly they cannot change too quickly here, right? Otherwise, if they change too quickly, then that's erratic functions like that. with small h's this not normally happens. So that's a checkpoint here. If all of a sudden I found 17.4 here, I know, oh no, this cannot be this. This should be much closer to the previous one. Okay, so I'm rather confident that I made minor mistakes. Okay, so we are there. So now the third row. Okay, what is this one? Well, that is add another 0.5 to it, and we need to the calculation for y3 is, well, y2 plus h p times x2 y2, and we have all components, right? That's 1.7814 plus h is 0.05 times minus 2.6952. Okay, let me do this with my calculator again. So let me clear this. Minus 2.6952. Multiply this with 0.05 and add that to 1.7814. I get 1.6466. Now, if your numbers are slightly different than these ones, then don't worry about it. The rounding errors very easily happen here, and that's why this method is a bit delicate. I discussed this in the end of the lecture video. There are two types of errors. There are three types of errors, of course. We also make errors, right? But if everything is done correctly, there's still rounding errors that come from using either 2 digits, 4 digits, 8 digits, or whatnot. And the other errors comes from the steps, the size of the step in this point, 0.05. Okay, so that's all. So our conclusion is that y3, because they asked us only to do 3 steps, if I got that right? And so give me a sec here. I'm going to look at. I think I have the solutions. I don't know whether the solutions. Just want to double check that I didn't make a mistake, or not an egregious mistake. This was number 3, right? Yes, number 3. So apparently, according to the back of the book, the answers were 1.9, 1.7813. Well, I rounded it, so that's why I have a 4 here, and 1.6466. Yes. So I get exactly what the book says, except, like I said, here the rounding can make slightly differences, but that's minor differences, and I'm not going to concern myself. That's not important for us. Okay, so that's one example. Now let's do the other one. That was question number 13. But I asked you to do much less than what the book asked, which is a bit annoying because then you cannot tell at the back of the book, it gives you the full answer, but not what I ask you to do. So we have the equation is y prime plus 3y equals 7 e to the minus 3x, and we take the point 0.06. So this is x0, this is x1. I'm writing it now, y0, sorry. I'm writing it now as a point because that's really what it is, right? So remember, we have this direction field. So there's another thing we could do, of course, is we could write this as in a direction field, and we have at least a feel of what it would be. So let me do this just to illustrate how you would do this. So here is my direction field. I have set, you see the sizes of the t and y go from 0 to 2, because that's where we work normally, right? What was the initial condition here? Oh, x0 is 6, so I should not, okay, I'm going to have to adjust this. But let me first punch in the actual equation here. So this is minus 3. Be careful, this one is a little bit more finicky about using multiplication and so on than Wolfram alpha. Wolfram alpha is a much more intelligent interface. It understands much more different kind of inputs and intended inputs. Here we have to be really precise. So that's why I have put a star there for multiplication. Plus 7 star, because I'm going to multiply again, e to the power minus 3, and again a star, otherwise it will not tell me, and the variable is t, right? Okay, so graph direction field. Okay, this is my direction field. Now, remember, we were doing this as the x-axis should be the t. The t here is from 0 to, well, we will go only with steps of, so let's make this one here actually, well, let's make it, we're gonna do 2 steps of what's the step size here? Well, they ask you to do it in 3 different ones. I'm not gonna do that. I'm gonna do 0.1. So after 2 steps, I will be in 0.2. So let me put 0.4 here. Oh, that's not the point. So the t will from 0 to 0.4. We're going to go only halfway, but then you have at least a bit of a view. And then the y value, well, we have to start at 6, right? Yeah, at 6. So I'm going to put here from 5, and then maximum, I don't know exactly, so I'm going to put 7 here. But that might be not enough. The problem always with the y scale is that you don't know where you end up, right? So you might have to adjust this. So this is how it looks like. Where are my, why don't I have, all of a sudden my XY thing don't have a, I guess it doesn't like this 2, 4. Let me put here 1 here. Okay. Okay, now at least I get 1 scale here. I wish I had a little bit more scale. So let me also make this. I guess he likes to start from 0. So okay, so now I have a little bit more scale. I'd like to have a bit more fine-tuned scale in the bottom here. The arrow length, is that? No. Okay, it's fine enough here. So remember, our point that we're going to start up is this point, right? Oh, let's put it down that I don't like. Okay. So, okay, and so we are looking at 0.2. So somewhere, it should be somewhere, from what I can see, somewhere between 3.5 and 4.5, if we were correct. Just looking at what this predicts. Okay, so let's do this. Well, let's first do this. It asks you to do this, so I'm going to do only h, as I said in the thing, only do h 0.1. I asked you also to do other 2, but I'm only going to solve one because it basically is just changing the numbers and then looking at what happens at these numbers. But let me only do 1 here, and but 2 methods. First, Euler's method, the original method from Euler. Euler, by the way, I don't know whether you know who Euler is, but he's a German mathematician, and he's famous for many things. For instance, the E is sometimes, I don't know whether it was called after Euler, but Euler had this very famous formula involving pi and I and -1, this one. This is sometimes Euler's formula. E to the pi I complex number is 1. -1. Sorry, let me write it again because it's so this is Euler's formula. Not that we're going to use this, but e to the pi I is -1. But Euler is not only famous for that. He did many things. If you take discrete math, you will see also that he's basically the one that introduced graphs. Graph theory is the founder of graph theory, and so he's really a very important mathematician, and he has applications in many different fields. And in this field, he did this method here of trying to solve differential equations. Okay, so what we need to do, well, the Euler's method, we always have to write this in the standard form here. Well, no, I shouldn't say always, but this is the form we want, right? And then we have our little table again. So these are the steps. It's 0. This is xi, yi, and that is p of xi, yi. So 0 and 6, right? That's where we started. The point 0.06 here. So let's calculate what the p-value is. So that would be putting 0 there. So if I put 0 in here, so x is 0, y is 6, right? I get -18 plus 7. Yeah, okay, that's minus 11. It goes down very steeply. Minus 11 is a rather steep downwards curve here, if you want to see here. It's perhaps not exactly, it doesn't look to minus 11 here to me, but I guess, okay. Okay, so we know that. So we know that y1 is, well, x1 is of course, you add, what was the step? 0.1, so this is 0.1. And y1 is now y0 plus h times p x0, y0. I'm writing out the general formula, and now I plug everything in. That's everything that is in this line. So that is 6 plus 0.1 times minus 11. So that is 6 minus 1.1. That would be 4.9. Okay. So let's figure it in. So this was 0.1. This is 4.9. So we need to calculate the value here. So now in P we're now gonna plug in these two coordinates here. So x is 0.1 and y is 4.9. And again we need to fall from alpha for this. Let me see. Yes, okay. I can over from alpha. So what I have to calculate is, let's see. Where is my equation here? Okay, so minus 3y. Oh, I need the values. I didn't copy the values for y. Okay. Sorry. X1 was 0.1 and y1 was 4.9. Okay. So here comes 4.9 then. And then the other term was plus 7e to the power minus 3 times x, that was 0.1, right? X is 0.1, yes. Times 0.1. Here I write it times because otherwise I don't know whether he understands my writing here. If I write minus 3 and then just 0 and 1, he will just think it's minus 30.1. So sometimes you have to write a multiplication there, but often you don't need to. He figures it out himself. So according to this, it should be minus 9.5, but let's see whether he calculates what I want him to calculate. Where's my equation here? Sorry, I'm looking at the equation. Minus 3 plus 7 times e to the minus... I think this is correct. So we have... y prime at 1 is minus 9.51. I'm just going to write the 2 digits here. So minus 9.5. Let's just do 1 digit, minus 9.5. And again, it's relatively close. It's not I jumped all of a sudden to 17 or something like that. So I'm rather confident that this is correct here. And then finally we need to calculate, I asked you to do just y1 and y2, okay, rather than all 10 of them. So what would that be? So, okay, the next step would be 0.2 for x, and for y, well, now we need a formula, right? y2 is y1 plus h times p, x1, y1. Now, the calculation of x1, y1 comes from using the data of this row, right? Okay? So this row will calculate me the data here. So this is y1 is 4.9 plus 0.1 times minus 9.5. And I'm going to use my calculator again to do that. So I have 9.5 negative times 0.1 plus 4.9, and I get 3.95. So this is 3.95. And I only asked you to calculate this number, so you don't need to calculate this part anymore. That would be, we need that one that I just indicated for the next one, for y3, but they didn't ask you y3, so this is fine enough. So this is the value that I find here, and looking at the picture, we said it was going to be somewhere around 4, something like that. So, okay, doesn't sound too bad. Let's see here to my picture. right? So I would be somewhere, oh, yeah, and unfortunately, I don't know why it doesn't show you 0.25, but you can imagine it's somewhere halfway here, so it's somewhere here. Yeah, you cannot see where I clicked, so, but it sounds to be kind of correct. Okay, so, but this was one method, so this is one method. Now I want to do the semi-linear method. Euler's semi-linear method. Now, the name semi-linear, let me not address that. It comes from because you're using kind of the same thing as in linear differential equations, namely you solve the homogeneous one and then you do the parameter. The Euler there's some work to be done. So first we have to look at the homogeneous one. This is the complementary, so the complementary homogeneous, that is this equation, right? And that we have to solve. We have to find the general solution for that. This is very simple. It's always, we know that it's going to be always separating variables, so dy over y equals 3 dx. So this means that ln of y is going to be 3x plus a constant. Yeah, I said when we're solving this, we would use the general solution. But remember, I'm actually now going to apply this to the semi-linear method. In other words, to the particular solution, so I don't need to write the constant here, the integration constant. So we'll not need the constant. That's why I'm not writing it. It saves me a little bit headache, okay? Now I have to solve here, of course, we do the exponentiation here that y is e3x. And then the method says now, this one is homogeneous, so you take u times that homogeneous. So this is for the particular solution. So this is if I want a homogeneous solution, not all of them. There would be another constant here that I didn't take care of. And then, and now here, the particular solution. I remind you very quickly, this looks like this, right? Is u times the homogeneous. This was the homogeneous one. And now we do u times that. And this is now, will become a differential equation in u. So we get a differential equation in u if we work this out. Okay, well, for one thing we have to find y prime. That is u prime e3x plus u3 e3x, chain rule, right? That's where the extra 3 comes from. Plug this into the equation, we get u prime e3x plus u3u e3x, that is y prime. Now minus 3y, minus 3u e3x, remember this is yy, and that is equals to 7e to the minus 3x. Minus 3x? Yeah, okay. Oh, I see here. I made a mistake here, right? This was a plus here. There was a negative sign here. Yeah, I copied it wrong from this one. I'm so sorry. So that's why there's a negative sign. So this is supposed to be, yeah, here this is correct. But it is here that when I started calculating, so there's a negative sign, there's a negative sign, there's a negative sign here. So this would be a negative sign, this would be a negative sign, this would be this would be a negative sign. Don't forget there's also a negative sign here, negative sign there, sorry. So this is negative, this would be minus 3, this would now be minus, so that would be plus 3. No, I mean, sorry, I said minus, no, it's just plus 3. Here. Okay, plus 3 times u, which is e, yeah, and then, yeah, okay, so now we see that these two cancel, and we see that u prime e minus 3x is 7e minus 3x, but the e minus 3x cancel. What happened to my favorites? Okay, which normally doesn't happen. So this is a very, very special case. So u prime is 7, what this means that u would be actually 7x plus a constant, but we're looking out for some solution. So we might actually be able to solve here, and then we know that the actual solution would be, or at least one of the solutions would be 7xe minus 3x. There's a constant that we still have to figure out here that I kind of ignored. But that's not the point. The point is now that if we do the method on this one, what is happening here? Let's think about the semilinear method that we do on this one. So in some sense, I assigned this problem, but it is not really a problem on the semilinear method because it becomes so silly, right? Let's think about what happens here. So we now have to make the table here. Here would be xi still. Here would be ui, right? And this would be, well, p, but this is just 7, right? This is a constant, right? The form that you always have is, we have to write it in this form. Now we're doing, instead of y, our function is now u, so we write u prime equals what? And well, we say it's 7. So this is constant here. And now everything becomes much easier, right, to fill in. So let's see. What is x0 was at 0? What was u0? Oh, now we have to be a little bit careful, right? What is u0? We have to, let's plug in x equals 0 in here. So y0 is u0 times e to the minus 3 times 0. So let's just put 0. So we see that y0 is same as u0 and y0 was 6, right? Yeah, y0 was 6. So in this case, we see that u0 is equal to 6 as well. But it could be different, right? It depends on remember, u and y are different. Okay, so this is 6. What is this then? Well, it doesn't matter what you plug in, it's always 7. So this is going to be a very easy column. This is normally the hardest column to fill in. Okay, so you might say, well, nothing is happening now. This is always going to be 7. No, some things are happening, right? So let's see here. This was step 1. Step 1, we get 0.1 here. What is u1? Well, the formula says it's u0 plus h times whatever we have normally here, but this is going to be 7. So that's the whole point, right? In the formula, where is my formula here? In this formula, okay, here, let's say, we have this p in general depending on both x and y, but here it depends on nothing. It's just a constant. And so we're going to have, this is going to be the formula, 7h. So what is u0 was 6 plus 0.1 times 7. So what is that? That is 6.7. Right? Okay, 6.7. So this is 6.7 and this is 7. Well, we know that already. This number is different than this number, Professor. How can it be? Well, because you plugged in what? This is u. Remember, y1 is u1 times e minus x1 minus 3x1. This is a formula. This is a formula for u, for y. So y1 is u1 and you plug in x1 here. Let me perhaps make this, I was a little bit sloppy. Let me write this neater. E to the minus 3x1. Okay, so there's some calculation to do here. So u1 was 6.7 times e to the minus 0.3. Right? 3 times 0.1 is 0.3. So this one I have to do with my calculator. 6.7 times e, open the parentheses. No, this is, sorry. Let me do this. Clear everything. Come on, clear. Okay. E. No, I see. Some calculators have a weird way of calculating things. So let me give me a sec here. I have to find my bearing with this calculator. Okay, so now I do this E. Okay, and now I multiply this with 6.7, and it's 0.74. No, that's not possible, right? No, I made a mistake. Let me do it over again. I don't think I cleared my memory. 0.3 with a negative sign, and now we do the E of that, and we multiply that with 6.7, 4.96. So this becomes 4.96. That's y1. And let's compare with, we had 4.9. You see, we're not that far off. And let's do now, what is the next one here? because I said also do the second one, right? So y1 we have calculated. Now y2 will be u2 times e to the minus, what comes here? Well, x2. What is x2? Well, that is one step further, so there will be minus 0.6 here, right? Minus 3 times x, minus 3 times 0.2. And what will this be? Well, this is 7, but we don't need this. What is this one? So that's the only calculation we have to do. u2 is u1 plus h times p of u2 and u0, but that's just 7. So again, it's very simple, right? So u1 is 6.7 plus 0.1 times 7, so this will be 7.4. And so what is this then? This is 7.4 times e to the minus 0.6, so that's the one I have to calculate. Clear everything, okay, 0.6 with a negative sign, then exponentiate, and then times 7.4, and I get 4.06. So this, okay, let me write the y values here, right? This is the table that we use to calculate the various things, but here's an extra part. Now in the semi-linear we have one more column that comes from this multiplication of these two, right? That is, so here this was 6, right? That was the initial value. At 1 we calculated was 4.96. And here we calculated 4.06. So if you want to complete the table here, and comparing where we had, again, it's not too far off. Okay. In fact, they ask you to discuss what you think is going on here, and without going too much into detail, what is really going on is that in this question 3.113, so these values that you get here, these values that you get using the semi-linear method, no, this is not where I'm pointing. Sorry, here, the semi-linear, these values are actually the correct values. And the reason for that is because we said the error is in terms is proportional to h. The total error is proportional to h, to 0.1. But what is the proportional constant depend on the second derivative? Now the second derivative of u, if u prime is 7, the second derivative of u, right? I'm talking about u, I'm the semi-linear one. If I look at u double prime, that is 0. So in this method that I used here, I'm using Euler method on u. The second derivative is 0, so the error is 0. So the u values are correct. These are the correct u values, and therefore the y values are correct, because they're just coming from the formula, the original, this formula, right? So this sometimes you this Euler's method, the Euler method itself was not correct. These values are not correct, because if I say that these are correct, then these cannot be correct because they're not exactly the same, right? But the semi-linear is actually completely correct. You see how drastic different the Euler method and the semi-linear Euler method can be. And then, so I'm not going to, as I said, that's all I want to do of this this topic. You see, it takes a long time just to do all the calculations, but I hope you get the gist of it. I'm not going to do more of it. 3.2 and 3.3 are sometimes also offered as part of this course, but I invite you to read them, and then you see there are even better methods that get better results.